Okay, let me know if you're not able to see this question. I'll increase the size. So the question is that there's zero point 0.2 moles of hydrogen gas and 0.15 moles of iodine gas, and they're heated uh, until equilibrium is established. This is the reaction that's happening. So let me copy the reaction over here. It's H2 reacting with I2, and it's in equilibrium with 2HI. So that's the reaction that's happening over here. And he has said that zero point 0.2 moles of, so those are your initial moles. So your initial moles are that you have 0.2 moles. So you have 0.2 moles of H2 added, and you have 0.15 moles of iodine. So that's those are your initial moles, and they're heated. So there is no HI added initially. Okay, so these are your initial moles. Then equilibrium moles. Now you are provided with this thing that at equilibrium it was found that 0.26 moles of HI hydrogen iodide were present. So at equilibrium you have 0. So you have 0.26 moles. So you started off with 0 moles and now you have 0.26 moles. That indicates that 0.26 moles must have been produced in the reaction. So 0.26, they got produced. Now that would indicate that 0.26 are getting produced. That would indicate that a reaction must have taken place, and it's 2:1. So that means if 0.26 are getting produced, that means 0.13, 2:1, use the ratio. So 0.13 over here must have reacted.
Sir, I didn't get this. Okay, how did you get 0.13?
एक second बताता हूँ. नहीं, is this clear? कि initially you had 0 moles, ठीक है, HI.
Yes, yes.
And at equilibrium, you figure out, well, you put them all in a container, and a reaction happened forward, backward, etc. They started happening, and at equilibrium, you figured out that they were 0.26 moles. So that means where did the 0.26 moles come from? They probably came from when these two reacted, and they ended up producing HI, right?
जी.
Okay, so that's where the 0.26 moles are coming from. So to produce 0.26, how much I2 and how much H2 must react? It's
1
two.
mole.
It's 2:1. So to produce 0.26, it should be 0.13.
अच्छा, alright, सही. ठीक, ठीक, ठीक.
So according to the ratio, I mean, if you wanted to produce
अच्छा,
two,
in case if the moles of hydrogen and iodine were different, so what would we be comparing with it then?
they were different. Why would they be different? Like
मतलब
different.
in case if there was a reaction where the reactants moles were different from each other, then how would we know to compare which with
Okay, I
which?
mean, this thing. Okay, let's say this is 2H2, right?
Exactly, जी.
So in that case, you're going to do the same thing. It's two to make
Mm-hmm.
two H2 would react, right?
Hmm.
So to make two H2 would react, right? So to so 0.26 over here should have reacted.
अच्छा, and in iodine it would be 0.13 then.
According to the ratio.
अच्छा, ठीक, सही.
Okay. Taha, your answer I think is correct. It's so anyway. So coming back to the answer, you started off with 0.15 moles, and now you have 0.13 that have reacted. So you're left with 0.02 moles. Okay. Mics, please off कर लो. So it's going to be 0.02 moles. And over here, you started off with zero point 0.2 moles, 0.13 have reacted. That means you're left with how much? 0.07 moles. And those are your equilibrium moles. And the final thing is what you have to do is you have to write the Kc expression, and the Kc expression would be it would be HI concentration squared, and the whole thing would be divided by H2 concentration and I2 concentration. Okay, the coefficient is 2, so it's going to be squared. So it's going to be 0.26 squared divided by 0.07 into 0.02, and the answer is going to be, it's going to be C. Okay, is this clear to everyone? Rita, is this clear? Abba, is this clear?
Yes.
Yes.
Yep.
So then the next one is, second. Okay, so the next one is, you're given two equilibrias, and if you look at the two equilibrias, they are exactly the same reaction. Uh, I mean, remember a reaction, whether it's the forward or the backward reaction. I mean, for example, you have the Haber process. Uh, the Haber process is N2 plus. Uh, I mean, not the. Let's go with this equilibrium. Okay, I'm just giving an example. So 2SO2 plus O2 in equilibrium with 2SO3. Now remember, in an equilibrium reaction, there are no reactants. There are no products. These are just conventional terms that are used because the reaction has. I mean, the forward. Who's going to? I mean, it's an arbitrary decision whether the forward is forming the products or the backward is forming the reactants. I mean, that's an arbitrary decision. I mean, the whole reaction could be written the other way around as well. It would mean exactly the same thing. Like 2SO3 could be turning into 2SO2 plus O2. This could be your reactant and this could be your product. But both expressions are exactly the same. They are representing exactly the same reaction. Okay, so uh, remember this that when you're talking about equilibrium or reversible reaction, the reactants and products are just arbitrary notations. The left side one is the reactant, the right side one is the product. When in fact there is no reactant, there is no product. The product is forming in the forward direction. The product is also forming in the backward direction, right? So it's just a conventional term that's used. Uh, is this point clear? Okay, these two are exactly the same reaction.
Yes.
But then there's the thing that if these two are exactly the same reaction, using conventional terminology, the Kc value is going to be different because Kc is specifically products over reactants. So if I write the Kc expression for the first one, uh, even the values that go into the expression would be exactly the same, but the expression is going to be different. The product term comes in the numerator, so it's going to be SO3 concentration, and that's going to be squared, divided by the reactant concentration, which is going to be SO2 squared, and O2 would be power 1. Let's call that Kc1. For the other reaction, let's call that Kc2. Because you're using conventional notation, the Kc expression is going to be different. Okay, in this case, in Kc2, the SO2 concentration is going to be in the numerator, and the O2 concentration would also be in the numerator, and SO3 concentration would be in the denominator. Okay, so the point is that both expressions would come out to be different. They would be using exactly the same values because they're simply the same reaction, just written the other way around. So their concentrations would be exactly the same. The concentrations over here in the reaction or over here in the reaction would be exactly the same. You're just using different ways of representing the reaction. But that would affect the Kc value. Now, Kc1, I mean, what would be the relationship between Kc1 and Kc2? Since they are using exactly the same values, Kc1 is just an inverted Kc2. Like if you take the inverse of Kc2, I don't think that's the right mathematical term. If you just make it upside down, it's going to be Kc1, right? So so that's the relationship between them. Uh, they represent the same reaction. The only problem was that you had just written the reaction the other way around, which gave you different expressions for Kc1 and Kc2, but they were still linked by some relationship. ठीक है, is this point clear?
Yes.
Yes, sir.
ठीक है, so it matters how you write a reaction. I mean, that's going to affect the Kc output that you're going to get. Now over here, it's the same reaction. If you look closely, reaction 1 and reaction 2, they're exactly the same reaction. Okay, there's no difference. It's just written differently. That's the only difference. Like x2 and y2 are reacting to produce x2y. This is the same. x2 and y2 are reacting to produce x2y. The mole balancing is different. I mean, what I could have done over here was instead of writing 2, I could have instead written half over here, right? I could have divided the whole equation by 2, and I would get balancing in terms of half. Uh, and that would make the expression even different, even more different. Like SO2 concentration would then become power 1, SO3 concentration would become power 1, and O2 concentration would become power half. And that indicates that it's being underrooted. So the same thing is happening over here. And what you just need to do now is you need to figure out what the relationship is between Kc for 1 and Kc for 2. That's the challenge. What's the relationship between the two? Uh, so write the expression for the first one. They're exactly the same reaction. For the first one, for the first one, it's going to be, let's talk about that as Kc1. It's products over reactants. So X2Y concentration, that's going to be squared. And then you're going to divide that by X2 concentration, that would be squared as well. And Y2 concentration is going to be power 1. Okay, that's one expression. Let's write the expression for Kc2 and let's try and figure out the relationship between Kc1 and Kc2. So Kc2 is going to be the products are X2 concentration, and that's power 1, and Y2 concentration, and that's half. And the whole thing is being divided by the reactant, which in this case is X2Y concentration. So what's the relationship between Kc1 and Kc2? So what I'm going to try and do is I'm going to try and convert Kc2 into Kc1. The first thing I'm going to do is I need to invert it. Okay, let's make it upside down. So what I'm going to do is I'm going to take Kc2, make it. I'm going to invert the whole expression. It's going to become 1 over Kc2. To do that, this whole thing would get inverted. This would go on top, and this thing would come at the bottom. Right? So that's the first step I've done. Now the expressions kind of look similar. Okay? So I'm going to try and make this expression look exactly like this. Now the other thing I need to do is I need to square it. Why do I need to square it? Because x2y over here has a power of 1. Over here that's squared. And x2 is also squared, and y2 is power 1 over here. Over here it's half. So that's also getting squared. So I'm going to square everything. So if I do that, this would become squared. This would also become squared. And this one would just become power 1. It's going to become power 1. So now the two expressions look exactly the same. Okay, so I converted this Kc2 that I wrote and I manipulated it to look like Kc1. So that means Kc1, what's the relationship between Kc1 and Kc2? Kc1 is basically equal to 1 over Kc. Kc1 is equal to 1 over Kc2, except that it's getting squared. Okay, that's the relationship between the two values. Is this point clear?
Yes.
Yes.
Yes, sir.
And the final thing is that he gave you the value of Kc1, which was 2. So that means 2 is equal to 1 over Kc. This was Kc2 squared. Okay, so get rid of the square first. So you would have to under root it. And then Kc2 would be, if you turn the expression around, it's going to be Kc2 would be 1 over 2 under root. And that's going to be your answer to this question. Okay? So it's A in this case. Right? Is this clear? I said then, and this is a very important point. Remember, always remember
Sir,
that.
is it A or C?
A.
नहीं मतलब K1 is equal to 2, so 1 over K2 square wouldn't it be C? मतलब 1 by 4. 2 square is 4.
No,
So I guess
this was 2.
hmm.
Kc1 was 2, right?
G.
Okay, so how do you get? I mean, I wanted Kc2, right? So I had to make Kc2 the
Hmm.
subject of the equation. Okay, so this was 2. So first thing, get rid of the square. How do you get rid of the square? You under root it. So that became 2 under root is equal to 1 over Kc2, right?
Oh, ठीक सही.
So then you have, one second. So now the next thing is, but remember this is a very important point that I mean you could have different Kc values for the same reaction. It's just how you balance the equation and how you write. I mean, if you balance the equation differently, you get a different expression for Kc. If you write the reaction the other way around, you get a different value of Kc. But all the Kc values would have some relationship between with each other. So anyways, this one is an easy question. You just have to figure out the unit for Kc. Remember that I told you that that don't simplify concentration, just take it as x. So the product is y squared into z cubed. So that is x squared into x cubed. And the whole thing will be divided by the other unit, which is the concentration of x and concentration of w. So that's w into x squared. So it's w into x squared. If you simplify this, the end result would be you're going to get x squared. X was concentration. So that's mole per dm cube squared. So it's mole squared and dm minus 6. Okay, so just use concentration as x and then simplify. As anyways, so then you have this question, which I think we did previously as well. Now this question is that it says the problem with this question is you have to try each option because every time they're asking for the equation. They've given you that 2 moles of P were placed in a vessel. So they've given you initial moles, they've given you the equilibrium moles. What they haven't given you is the equation. So that's a bigger problem because if the equation is not with you, you would have to try each one separately. So I'm going to look at option A first and see if the data matches. If the data matches it. So let's go with A first. A is P in equilibrium with it's in equilibrium with the what with 2q plus r. Okay, so that's the first option. Now they're saying that that initially 2 moles were added. So I'm going to write the initial moles. It's 2 moles. And there are no moles of, there's no Q, there's no R, nothing. That's your initial moles. And then they're saying that compound P was partly decomposed on heating and a dynamic equilibrium between PQ and R was established. So it was partly decomposed. Some reaction happened. So there would be some Q and there would be some R. And at equilibrium, they figured out that there was X moles of R present. So this is what's happening at equilibrium. That you have X moles But that's your equilibrium moles. Now, in terms of X, we need to figure out the equilibrium moles of all the other substances. So how would you do this? What you're going to do is, okay, initially you had 0 moles. Now all of a sudden at equilibrium you have X moles. That means X moles got produced. So X moles must have been produced in the reaction. So if 1R is produced, 2Q would be produced. So if X moles of R are produced, that means 2X moles of Q must have been produced. Okay, so 2X moles of Q must have been produced. It's 1:2. And if X moles are produced over here, then it's 1:1. X moles of P must have reacted. So over here, X moles, they probably reacted. So what are your equilibrium moles now? Over here, it's going to be 2 minus X. Okay, that's going to be your equilibrium moles. Why? Because initially you had added 2 moles. X moles have reacted, taken part in the reaction. So you're left with 2 minus X. You had 0 moles, 2X moles got produced. So that indicates that there would be 2X moles at equilibrium. Okay, Taha, I'll just quickly check B after this. So I finally figured out the moles of the reactants and the products at equilibrium. Okay, these are the moles that I'm getting. But are these the right moles? Because the question had stated that the total number of moles present at equilibrium was 2 plus X. So if I sum them all up, I'm not going to get 2 plus X. I mean, if you do this, if you sum them up, what do you get? You get 2 plus 2X. Because 2 minus X plus X, the X gets cancelled out, and then there's another plus 2X moles. So that's a total of 2 plus 2X moles. And they had specifically stated that you're going to get 2 plus X moles in total number of moles. So which is why A is not the correct option. Okay, so Taha, I'm going to go with your option now. Okay, now your option has a different quantity of moles. It's 2P and 2Q and 2 and R. So if I use those, the rest kind of looks same. It's only this is 2P. So if X moles are produced over here, 2X moles must have reacted. Right? 2X moles must have reacted. Why? Because 1R is produced by 2P. So X moles are produced by 2XP, double the amount. So the amount of moles over here would be, they're going to be 2 minus 2X. So they're going to be 2 minus 2X. And now if I add everything up, then you can see that the total number of moles, 2 minus 2X plus 2X, the 2X gets cancelled out and you're left with another X. So that's going to give you 2 plus X moles. So that's going to be the correct answer. It's going to be option B. Is this clear to everyone?
Yes,
Yes,
sir.
sir.
Ethan, Mohammed, is this clear?
Yes.
Now a few things that probably haven't been mentioned so far is I'm just going to add a few things, although it doesn't really often come in questions, and that is just a couple of points. One is that if a solution is aqueous, Okay, so if a solution is aqueous and water is involved as a reactant or a product, so water is involved as I say, so water is involved as a reactant or a product. You're not going to write water in the expression. ठीक है? Take water's concentration as 1. So water's concentration is taken as 1, and the reason for that is okay, whenever something is in a large excess, its concentration almost becomes constant. So for example, you have a reaction in which water is involved. Let's say there's H2O2, and it's in probably let's think of another reaction. Let's think of a halogenoalkane reacting with water, and it's in equilibrium with a displacement reaction happens, an alcohol forms, and HCl gas is produced. Okay, let's assume this reaction is taking place. Now, the thing with this reaction is that you have water as a reactant, and let's say all of them are aqueous. Now, if everything is aqueous, that would mean that water is in a large excess because any solution that's mostly water. So there's a lot of water. So for example, there's 0.1 moles of halogenoalkanes, and there's let's say 0.3 moles of alcohol that's being produced, and there's let's say 0.3 moles. These are just hypothetical numbers. Okay, so 0.3 moles of HCl being produced as well. The amount of water, because the whole solution is water, everything is dissolved in water. The amount of moles of water would be very large. So for example, you have 200 moles of water. Okay, any solution is mostly water. So the amount of moles of water would be in a large excess if the solution is aqueous. No, this is only Taha. This is only for solutions. Only for solutions. Okay, if you look at any solution, like if you see HCl aqueous or NaCl aqueous. Okay, so in that solution, there's actually very small amount of NaCl. It's mostly water. Okay, what is NaCl solution? You take a glass of water and you just add a spoon of NaCl in it, a spoon of table salt in it. That's NaCl aqueous. NaCl aqueous is mostly 99% of it is basically water. There's just 1% or 2% salt that's added to it. The same is with any aqueous solution. If you see HCl aqueous is mostly water. Just with 1 or 2% or 3% of HCl molecules added to it. ठीक है, Taha, is that point clear? Achha, so the point is, okay, whenever you have an aqueous solution, that means you have a lot of water. And when you have a lot of water, when you have water in large excess, its concentration almost becomes constant. ठीक है? Just imagine, let's say the equilibrium shifts to the left. ठीक है? And all of a sudden, let's assume the equilibrium completely shifts to the left. ठीक है? If it completely shifts to the left, all the 0.3 moles they have reacted, they're gone. So what would happen? 0.3 moles would react with 0.3 moles to produce how much CH3Cl? 0.3 moles of this. So an extra 0.3 moles got added, right? And they're going to produce, because it's 1:1, 0.3 moles of water would be produced as well, right? So over here, the difference is a lot. Like the CH3Cl amount, it increased 4 times. Like it was 0.1 mole initially. Now the total amount of moles is 0.4. So that's an increase of 4 times. But what happened to the quantity of water? That initially you had 200 moles, and when the entire equilibrium shifted to the left, now you have 200.3 moles. So the difference in quantity of water is negligible. So it doesn't really matter. The water amount doesn't really matter if the equilibrium shifts backwards or it shifts to the right. The water is in such large excess that its quantity is almost constant. I mean, 200 moles and 200.3 moles are pretty much are almost exactly the same moles. Which is why, since water is not changing its concentration because it's in large excess, it's not even changing in concentration. You don't actually write it in the expression. ठीक है, is that point clear?
Yeah.
ठीक है, is this clear to you? Yes.
Yes, sir. In case if we do write it, would it matlab, make our answer incorrect or what?
The problem would be that it would have such a high concentration that this term would dominate. I mean, if you write it in the expression, so I mean, this one value would just make the whole thing a constant. For example, if you write, well, anything that's getting divided by 200, ठीक है, would be a very small. I mean, it's products over reactants, right?
Ji.
So anything that's getting divided by, like, if you have 0.3 moles, you divide by 200, you get a very small value. If this is 0.1 moles, you divide by 200, it's going to be a very small value again. So the problem with this, adding this thing, would be that the Kc value would hardly change because this is such a large number.
ठीक.
ठीक है? So it's you don't add this value. Anything that's in excess, and this applies to anything that's in excess, that is not written in the expression. Its concentration is taken as a constant, but it usually just applies to water. So if water is a reactant, you don't write it in the expression. But make sure that it's an aqueous solution. If they haven't mentioned it as an aqueous solution, then you have to write water. Okay, this only happens if the solution is aqueous. So just remember that. For example, in this question over here, they're asking you to find the value of Kc for the reaction, and there is water involved, right? There's an alcohol reacting with a carboxylic acid to form an ester, and a water molecule is produced. But at no point have they mentioned that this reaction is in aqueous conditions. So this is normal. You have to write the water concentration in the expression. Okay? If they had mentioned that this entire thing was happening in an aqueous solution, then don't write water. Okay? But in this case, you're going to write water. And the second point is, just like water, the second point is that solid concentrations are going to be taken as 1 as well. Because if a substance is a solid and it's part of a reversible reaction, then the particles are always tightly packed. The term concentration doesn't really apply to it because the particles, the moles per unit volume is always the same. They're always tightly packed. So which is why the concentration is also going to be always constant, and it's going to be taken as one. So remember both these things. So I wanted to try one question which was slightly more difficult. Let's focus on this question. For example, this one. Now, in this question, what you have is the given. What's the Kc expression? The Kc expression over here is products over reactants. So it's going to be. Now, remember, focus on this. Ag is a solid. Its concentration is going to be taken as 1. It's not going to be written in the expression. So it's basically the product is Fe3 plus divided by the reactants. The reactants are Ag plus 1. And the other reactant is Fe2 plus. So that's going to be your expression. Ag solid is not going to be written in the expression. Its concentration would be taken as as 1. A lot of people actually forget this and they actually write Ag solid in the expression. They get the wrong value. So anyways, if you focus on this question, uh, let's try and find the answer of Kc. So it's Ag plus 1 plus Fe2 plus, and it's in equilibrium with Ag solid and Fe3 plus. Okay, so Ag solid, the product, that would not be written in the expression. What are your initial moles? Initial moles that are given are that there's 1 mole of silver ions and there's 1 mole of Fe2 plus ions. So those are your initial moles. And no Fe3 plus, no Ag solid, right? And then they're saying that there was at equilibrium, it was established there was 0.44 moles of Ag plus 1. So this is your equilibrium moles. At equilibrium, you have 0.44 moles. That indicates that 0.56 are gone. So 0.56 are gone, they have reacted. And if 0.56 are reacting, it's 1:1. 0.56 of this thing would also react. 0.56 of Fe2 plus would also react, and that would leave you with 0.44 moles as well. And since everything is 1:1, 0.56 react with 0.56. On the other side, 0.56 of this and 0.56 of this would be produced. So that means the amount of moles, because you started off with 0 moles. So this is 0.56 moles. And this is also 0.56 moles. The other thing that you have to be careful about is that the equilibrium expression, it doesn't take moles. It has to be concentration. And in this question, they had given you that it was a 1 dm cube container, which is mentioned over here. So be careful. Don't simply put moles into the expression. It's always concentration. So to convert this into concentration, you would have to divide by 1 dm cube, which basically gives you the same thing. Okay, so everything is going to be divided by 1 dm cube, and which basically gives you the same value. And the expression would be, the Kc expression would be 0.56, and the whole thing would be divided by 0.44 into 0.44. Remember, silver solid is not going to be written in the expression. Okay, that will be taken as 1. Okay, or you can explicitly write 1 or just don't write 1. Doesn't really matter. Okay, is this point clear?
Yes, sir.
Okay, so just be careful with solids and be careful with this aqueous thing. Okay, most of the questions they're not on this, and be careful that don't put moles in the expression. Always make sure that you're putting concentration in the expression. I said there's one question which is kind of tough. I'm going to assign you that question. TK, send it on WhatsApp. TK, just 1 second. Let me try, and we're going to discuss that question tomorrow now. But try and attempt that question. Pata nahi, just 1 second. It's probably somewhere, probably this one. So it's this one. TK, let me. I'm sending this question on WhatsApp.
Sir,
Yes.
could you send the whole paper as well?
Yeah, I'm going to do that.
All right.
Just 1 second. There's another. चलिए ठीक है. You can all leave. Let me post this on WhatsApp.
Chill, officer.
Okay, take care.
Thank you.
Thank you.
Thank you, sir.
Hafiz.